Welcome back. We are discussing charge flux, and this would most likely be the last class for that chapter. So, we're going to look at the charges or ions in solution. Okay. Many biological systems are solution based, and therefore, we need to have a good understanding of as to how to approach charges in this situation. Okay. So that would give us some reasonably complete set of tools to look at manipulation of charges, which we'll start doing in the actual context when we begin the next chapter. Okay. So let us see three important concepts of charges or ions in solutions in the context of charge flux. So, formally speaking, most cells are in an aqueous environment. Their contents themselves are fluid, and therefore aspects related to charges, ions in solution are important to consider. And three concepts we're going to look at. Okay. Uh, First one is electroneutrality. Okay. It's very simple, but quite often confused. So don't just look at what it is and apply it to wherever it's applicable, and don't get confused in out of the box situations. Okay. There are always situations where electron neutrality may not be valid, but given everything else, electron neutrality is valid in a solution, is what this says. Okay, let's go through it. Oppositely charged ions could be present in solution, of course. Okay, you have KCl, solution of KCl, very typical electrolyte. You have K plus and Cl minus ions that are present there. So oppositely charged ions could be present in a solution. There are strong forces of attraction between these opposite charges. And as long as the number of positive charges equals the number of negative charges, due to the strong force of attraction between the opposite charges, the net charge in that system is zero. Okay. So note every single aspect of this sentence is important to avoid confusion. As long as the number of positive charges equals the number of negative charges, due to the strong force of attraction between opposite charges, the net charge in that system would be zero. Okay. This is the condition of electroneutrality. In other words, electroneutrality is valid when the number of positive charges equals the number of negative charges. You go and introduce another deliberately a positive charge into that, then it's not going to be electroneutral. The solution is no longer going to be electroneutral. Okay. So you need to keep that clearly in your mind. Thus, and also there's another interpretation of this which is very important for us. An electrolytic solution which has opposite charges, equal number of opposite charges, K plus Cl minus for that matter, for example, cannot set up an electric field although it contains charges, because the number of positive charges equals the number of negative charges and they cancel each other. Okay. So a field is not set up by an electrolytic solution is one of the key things that is coming out of the principle of electroneutrality, which is certainly very useful for us when we start looking at things in detail to design aspects related on electrical aspects, to design biological systems, biological processes, biological tools based on electrical aspects. So this is electroneutrality. The second is a totally different concept. It's called charge relaxation time. Let's spend some time on this. Let us consider an electrolytic solution, which could be a medium, which is homogeneous, properties are the same, well mixed, isotropic, it doesn't change with direction, and conducting. Okay. So this is our electrolytic solution, the medium, which is homogeneous, isotropic, and conducting. Now let us say that a charge density of rho 0 is added to the above solution. Okay, this is net charge density, rho 0 is added to the above solution. Since the solution is conducting, the charge will be conducted away to result in a new equilibrium. That's quite straightforward. And we are going to estimate the time that it takes for achieving the new equilibrium. To do that, let us do this. According to Ohm's law, the charge flux is nothing but I dash equals Ke times the electric field strength E, equation 5.7.2-1, and E is nothing but minus of del of V, the electrical potential gradient, negative of that. The electrolytic solution is a homogeneous conductor that we've already said, okay, which means the conductivity is a constant. Now we take del on both sides, del dot, okay, pre-del dot I dash equals, take the constant to the other side, Ke times del dot E, equation 5.7.2-2. From Gauss's law, we know that del dot epsilon naught E equals rho, or del dot epsilon E equals rho for a medium. 5.7.2-3, rho is the charge density at any time t. And if we substitute 5.7.2-3, this equation, into 5.7.2, that is this equation, okay, we have a del dot E here, that's what we are going to replace using Gauss's law, Maxwell's first equation, differential form. If we do that, then left hand side is del dot I dash, which is the same as that, and the right hand side becomes Ke by epsilon times rho. Okay. Equation 5.7.2-4. If we assume that on application of rho 0, the increase in charge density in the solution is uniform, we can use the charge conservation equation and the charge continuity equation. Okay. So charge continuity has to be valid for any situation because charge is conserved. So del dot I dash equals minus dou rho dou t. This is the charge conservation equation, if you recall, 5.5, equation 5.5-5, that is this. Okay. So this has to be valid. So here you have del dot I from our consideration of Gauss's, rather Maxwell's first equation. Here you have del dot I from the charge balance equation, charge continuity equation. And if you substitute 5.5-5 into this equation, 5.7.2-4, this equation, left hand sides are equal, therefore you could equate the right hand sides. So you'll end up with dou rho dou t, you have a negative, no? So you bring both to the same side. Dou rho dou t plus Ke by epsilon rho equals 0. Okay. We'll call this equation 5.7.2-5. Okay. Very fundamental aspects. Charge conservation is as fundamental as it is. So therefore, the charge continuity equation is very fundamental, widely valid. This is nothing but directly from Maxwell's first equation, very fundamental equation. We applied both to solutions and we have come up with this equation, which gives us the variation of rho with time. The solution of this equation is nothing but rho equals rho naught exponential minus t by tau r, where tau r, this is 5.7.2-6, where tau r is epsilon by Ke, and this tau r, which is epsilon by Ke, is the charge relaxation time. Okay. So the solution of this differential equation from very fundamental considerations is this: rho equals rho naught exponential minus t by tau r. Recall your math equations, the form of the equation, the solution. And tau r is nothing but epsilon by Ke from, we have just combined epsilon by Ke as tau r. And this is called the charge relaxation time. For water, Ke happens to be about 0.01 Siemens per centimeter. Recall the units of conductivity, Siemens per centimeter. Epsilon is about 80 times the permittivity of free space for water. Okay, this you may recall from your working out of problems from your high school pre-engineering levels. Therefore, and you know that epsilon naught is 8.85 into 10 power minus 12 farad per centimeter, therefore it's 80 times that. Therefore, tau r is epsilon by Ke, and that turns out to be 0.7 nanoseconds. Okay, so you add a charge density, uniform charge density of rho naught into a conducting solution. In 0.7 seconds, the whole equilibrium is achieved. A whole new equilibrium is achieved. That's a great insight. Okay. So if you keep adding charges and expect some effects to remain there, it's all gone in 0.7 nanoseconds. Okay. Of course, to a new equilibrium, but it's all gone. And on the flip side, you don't have to wait long for the new equilibrium to be achieved, done in 0.7 nanoseconds. Okay. So these are the kind of insights that you can get. So charges can be relaxed rapidly, and charge relaxation needs to be considered while designing systems in which biological materials such as cells, biomolecules, and so on and so forth interact with electrical fields such as in electrophoresis. So in electrophoresis design, these principles are all embedded there. So electron neutrality, so no field is set up by the solution, that's a very essential thing, and charge relaxation. You cannot keep on adding charges to expect some manipulations in the dynamic aspects because charges are relaxed very rapidly. So those were two principles. We said three. The third one is called d by length. Okay. Say, to understand d by length, let us consider this. Say we have a specially made lipid layer with uniform surface charge density stretched on a flat plate at x equals 0. Okay, so x equals 0, so somewhere here you have the plate, you have a specially made lipid layer with uniform surface charge density, and we have stretched it out on a flat plate which stands something like this. The lipid layer, let us say, is bathed by an electrolytic solution with cations and anions. Okay, so there are charges on the lipid bilayer and there are charges around. Near the charged surface, because it is uniformly charged, mobile ions whose charge is opposite to that of the fixed charge will be attracted, right? So that is nature. Oppositely charged ions attract each other. So if you have a negative charge here, it is going to attract only positive charges close to the surface. In other words, near the charged surface, there is a region in the solution where electron neutrality does not hold. Because of this charge, it's going to attract the oppositely charged ions close to it. Therefore, there is a region where electron neutrality is not going to be valid in the solution. Okay, you take the plate and the solution together, yes, but in the solution itself, electron neutrality is not going to be valid. The region will be charged with the charge of the counter ions. And d by length is nothing but the length of this region in the solution near the charged surface where electron neutrality does not hold. Okay, that's it. So there is a very thin region. It turns out to be very thin later. There is a region close to a charged surface where electron neutrality does not hold in the solution. That length over which that region exists is called the d by length. And if you look at WISE, we have already seen this book earlier. This is Cellular Biophysics 1, Transport, MIT Press, published in 1996. He has derived an expression for d by length. I am not going to get into the derivation in this course. You can look it up. Here I am just going to state it as lambda d, which is the d by length, can be given as the square root of epsilon r t to z squared f squared c. Okay. And epsilon is the permittivity, z is a charge, f is the Faraday's constant, c is the concentration of positive or negative ions at infinite distance infinite distance in the solution where electron neutrality holds. Okay. So, epsilon, r gas constant, T temperature, 2z surface charge, f squared, Faraday's constant squared, and c is the concentration of positive or negative ions at infinite distance in the solution where electron neutrality holds. Okay. This is an important parameter used in a lot of design measurements and so on and so forth. So you need to know about this, about ions in solution. Okay. So in this chapter, we have looked at three important concepts related to ions in solution, charges in solution. First one was the concept of electron neutrality. Second was the concept of what did we do? Of course, we looked at d by length as the third concept. Yeah, charge relaxation. Charge relaxation, then d by length. Okay. Okay, we will stop here, and we have completed this chapter. When we begin the next class, the next class will be a review class of the concepts that we have seen in this chapter. See you then.